In this tutorial, we will walk through the process of setting up a WAGO PFC100 or PFC200 controller along with a WAGO Ethernet coupler. The PFC100 and PFC200 are both part of WAGO's Linux embedded controllers. Both controllers utilize the same operating system, and for that reason, the setup or workflow of commissioning a PFC100 and PFC200 controller remains the same for both devices. The PFC controllers support programming according to the IEC standard 61131-3 with WAGO's eCockPIT solution, as well as operating as a versatile Linux device. In brief, the PFC range of controllers utilize an embedded Linux real-time operating system with a real-time preemptive patch to provide multitasking and task prioritization facilities for your programming and also Linux applications to run in parallel. One thing to keep in mind, an embedded Linux OS is not the same as a typical Ubuntu or Arch Linux distribution. For more information, feel free to explore the information included in the description below, as well as looking to our website for further information. Embedded Linux, Docker, our Docker Hub, and also our GitHub account. Moving on, let's have a look at the process for setting up a PFC100 or PFC200 controller. The process for setting up our PFC controller will consist of an update to the firmware. Once the firmware has been updated, we will then explore the initial communication configuration using the WAGO Ethernet Settings Application. We will make these settings via the service interface using the USB serial communication cable. Today we have a 758-207 controller and a 750-352 coupler. If you haven't already, please ensure you have eCockPIT installed, which also installs WAGO Ethernet Settings and WAGO I/O Check. We will also use the free tools Win32 Disk Imager and the SD card formatter utility. We will now go through the process of installing the firmware on the PFC controller. In this case, we will utilize a bootable SD card. To prepare the SD card, first we insert it in our PC. In this case, I've previously written a bootable image to the SD card, so when we look into Windows Explorer, we see that the SD card actually is visible as two partitions. So what we'll do is we'll use the SD card formatter utility to return the original file system of the SD card. You can see it's already detected the main partition of the SD card. I'll give it a default name, SD card, format, confirm. Takes a few seconds. We see now we have a 1.93 GB FAT formatted SD card. Click confirm, close the utility. We'll now utilize the Win32 Disk Imager. We'll use this tool to write our firmware image to the SD card. It will also prepare the file system of the SD card to be bootable and readable by the PFC. So we'll go to Program Data, WAGO Software, eCockPIT, eRuntime, PFC, and select the firmware. In this case, the major revision is firmware 12. Click Open. It's already detected the SD card drive. Click Write. Confirm. This is writing the firmware image to the SD card. You'll also see in Windows, upon completion, we'll have the two partitions to the SD card visible again. You may be prompted to format the second partition. Please ignore this. We can now remove the SD card and insert it in the SD card slot of our PFC. This is identified under the clear cover of the PFC. With the SD card installed, we turn on the PFC, and on initialization, the PFC identifies that there's a bootable image written to the SD card, and now uses this as a temporary boot device. During this process, you'll see that an orange LED blinks or flashes from inside the SD card slot. You'll also observe the assist light blinking orange. This is indicating essentially a file system process where the device is now reading the information on the SD card and preparing it for operation. The process does take a few minutes, and during this process the sys light will eventually go solid green, followed by the I/O LED becoming solid green, and your run LED should also become solid red. It becomes solid red because we actually don't have any application on the system as yet to run. Once the process completes, we can then move to utilizing our Ethernet settings tool and using the service cable interface on the front face of the PFC to make our initial communication setup. Here are some summary notes which are included in the description to refer to. With our PFC booted up, we are now ready to set up our communication settings. We'll make these initial communication settings using the USB serial communication cable, and we'll access the service interface on the front face of the PFC. This interface is just below the SD card slot. My PFC is booted up. I'll load up Ethernet settings. I'll plug in the USB service cable. I'll then move to Settings, Communication. I'll select Serial Ports. I'll select my USB cable and click Apply. The application now reads in some of the parameters for the PFC, but not all of them. Only those which are configurable via the serial interface cable. With the settings read in, we can see the firmware version that's currently applicable to the device. Note, keep in mind that this is the firmware that it's booted on the SD card. This firmware isn't actually permanent on the device until we write it to the system. We'll explore this a little bit later. The IP address is waiting for a DHCP server, so unallocated, and the runtime system is based on Codesys version 2. So we'll configure the communication, we'll select the static configuration, and I'll select a nominal IP address of 192.168.1.17. We'll write these settings to the device. Keep in mind that since we are still booted from the SD card image, this process does take longer than normal. Once this completes, we should be able to ping the device using our Ethernet interface. While the device is writing the settings, we'll load up command prompt and we'll type in ping 192.168.1.117 to verify that we can get a reply from our device. Actually, the communication interface is already up and running, so we know that we're successful. You may need to set a static IP assignment on your PC. Keep in mind that this can't conflict with the controller itself. So now what we can do is, with the Ethernet settings application still open, we can click Run WBM. This will load up the web-based management for the system. We will need to proceed as the certificate may not be verified by your browser. Go to Web Page. And here's the web-based management for our controller. We'll log in. Default credentials are admin, all lowercase, and password, WAGO, all lowercase. Submit. You will be prompted to change the password. Until changed, that prompt will continue to pop up. Our first step is to go to the administration menu, create image, and start copy. In this case, the create image process is now looking to identify which is the primary partition. In this case, the memory card or the SD card is going to be the primary partition, and the create image process is going to work to copy from the primary partition to the internal flash. This process will make your firmware image permanent on the device. We'll click Start Copy, and the process will write the firmware image to the PFC permanently. When this is complete, we can power off the PFC, remove the SD card, and power back on the device. We now have permanentized the firmware image to the system. You will observe, while this happens, that the sys light blinks alternately between red and green. When it's complete, the sys light will be solid green again. The process finishes. The firmware image has been successfully copied. What we will do now is turn off the PFC, remove the SD card, and power it on again. You should notice that the device boots up significantly faster than when it was working off the SD card. With our device rebooted, we'll refresh the web-based management to confirm. We'll log in again since we would have been logged out. Same credentials, and OK. Now what we want to do is we want to switch the runtime system. So we'll click on PLC runtime, we'll nominate eRuntime and submit. Once again, this change happens a lot quicker since we're working off the internal flash now. Complete. This really concludes our initial setup of the PFC200. What we'll now do is we'll go back to Ethernet settings. I'll exchange the service cable from my PFC200 and plug it into my Ethernet coupler. I'll click read. Now reads in the settings for my Ethernet coupler. There we are, done. I've previously set this to 192.168.1.151. I'm happy with this. We'll select the protocols. We'll ensure Ethernet IP is deselected, and I'll select Modbus UDP and Modbus TCP. Nothing with Ethernet IP, we'll write these. It's also handy to know that we can use this interface to reset the factory settings and also reset the file system. We can now also load up the web-based management for our coupler, so we'll just directly punch in the IP address 192.168.1.151, and there's our web-based management. We can confirm password and user is the same as the PFC admin, and also WAGO. We can also generate our EA config, and we can see there's some channels attached to the device already. We'll now move to utilizing eCockPIT. So with the communication settings made to our hardware, we're now ready to utilize it within an eCockPIT application. So we'll load up eCockPIT. We'll start with an empty project. The default view is the network/devices, and on the right hand side we have our product catalog. We'll first search up our controller. I'll narrow it down by searching 758.207, and I notice that it's this device. Be careful that when you search the catalog that you select the correct device, since there are a number of variants of some of the devices with different part extensions, and the target will be distinctly different from each one. Once the device is added, we've prepared the environment for the device and any dependencies which are handled in the background. We can see on here some information at a glance. The default IP configuration is 192.168.1.1. We know that is incorrect, so we'll click on the device, switch to the settings over on the right hand side, and we'll change this IP assignment to 192.168.1.117. When we click away, that updates the device. We can now make a right mouse click and click scan. This now scans in the modules attached to the device using, in the background, WAGO IO check. In my case, I've got two 16-channel digital cards, an input and an output module. These devices have nothing special about them, so typically they're scanned as generic DI/DO. I'm happy with this. apply all and accept that selection. Double click on the device now, and we can see my physical I/O selected. I can also, while I'm in here, give some local variable names. So I've got my DI1, we'll just name the first 4 channels. I can also select the digital output module, and that really concludes my configuration. I'll switch back to the network. We'll also switch to the product catalog and add in my 750-352 coupler and add this to the workspace. Again, as the device, we'll make a link for communication. We'll click on the coupler, again switch to the settings, configure the IP address. My coupler is 192.168.1.151. Click to confirm, right mouse button to scan. There's a few modules attached to this coupler, including a 3-phase power measurement module and also a DALI multi-master module. I'm happy with that selection, so we'll click apply all. That concludes my basic setup of my network and hardware. What we will do is we'll switch to the programming structure. Default, my PLC PRG is inserted and I've got a structured text format. So I'll make a basic counter. We'll go I count and declare my variable on the fly, integer. Good. Now let's click program, connect. Now I need to enter my username, admin, my password, WAGO. And click yes to download and proceed. You'll notice that the application downloads to the controller, and we can also see that the current program is in stop, indicated by the red LED, both here and also physically on the device on the run LED. We click start, the application starts, all green, the run LED on the device is solid green, and our counter is incrementing. Let's stop this or disconnect this from this application. The application continues to run on the device. We're also free to use our local variables that we created on our hardware, XDI1, DI2, and etc. Thanks for watching.